Let's take a look now at the second derivative test. So sometimes called the second partial derivatives test. So suppose we've got a function whose second partial derivatives are continuous at near some critical point A. All right, then we're going to look at this quantity that we get, and we'll call it D for short, and it's formed by taking the product of the two double derivatives of f and then subtracting the square of the mixed derivatives of f. And then by looking at the sign of D and the sign of the second partial with respect to x at this point, we can determine if we've got a min or a max. So if D and the second partial with respect to x are both positive, then we get a minimum. If D is positive but the second partial is negative, then we get a maximum. And if D is negative, then we get a saddle. If D is equal to 0, then actually the test fails. It doesn't tell us anything, and so whatever's going on at this point is a mystery. It could be a max or a min or a saddle or an other. It could be something that's none of the above. So for an example of an other, just think about what it looks like when you graph x cubed in one dimension. Comes up and it flattens out and then it goes up again. And so sure enough, it has a horizontal tangent at the origin, but it's not a max or a min, and it's not a saddle. And so you can actually have the same thing going on in multiple dimensions. So in this case, imagine you've got something where it's going like a cubic this way, and then also as we follow the x-axis, it's doing a cubic thing kind of like that. So then you get, here for clarity, maybe I'll draw some like level curves of this function. Something like that. So it's kind of like a bump protruding out of a wall or something like that. Okay, so, oh, and by the way, if you're wondering like, hey, why is it the x derivative that's so darn special? What the heck? Well, it actually doesn't matter. You could use the second partial with respect to y as well, because if you look at this definition right here, if D is positive, then these guys have to have the same sign, right? Otherwise you get something that's negative. So you can choose either one. If D is positive, then fxx will be positive if and only if fyy is also positive. So you just have to check one of them. Okay, so that's the test. So to see how to use it, let's return to those examples that we just did in the previous clips. So the first one was x squared plus y squared minus 2x minus 6y plus 14. And in that one, we found that the gradient of f was, what was it? It was 2x minus 2 and 2y minus 6. So if we want to find the second partials, we'll find fxx by differentiating the first one, and fyy by differentiating the second one with respect to y. And then to find the mixed partial, we can differentiate the first one with respect to y or the second one with respect to x. But in either case, you see that we get 0. So, right, so for example here, d dy of 2x minus 2 equals 0. So that's the computation that I'm doing there for that one. Okay, so then our d is going to be 2 times 2 minus 0 squared, which is just going to be 4. Now, in general, d would be a function of x and y. In this case, since I took a quadratic polynomial and then I took two derivatives, I end up with just a constant. So this is a constant function, and it tells me that this function is always quote unquote concave up, right? But now in a higher variable sense. And that corresponds with what we saw before, right? So, oh, sorry, I should have said this fact, and also the fact that the second partial with respect to x is always strictly positive. So those two facts together tell us that the critical point 1, 3 that we found previously is a local min. If we look at the other example that we had, so x squared minus y squared, then let's see, so the gradient was 2x minus 2y. And so if we compute d, let's see, we'll need the second derivative with respect to x, so the partial of 2x is just 2, and the second partial with respect to y is going to be minus 2, and the mixed partial is going to be 0. So our d is 2 times minus 2 minus 0 squared is minus 4, which is always negative. And we have and then since it's negative, we don't actually need to check fxx or fyy, right? That's not part of the test in the case when d is negative. We just immediately learn that there's a saddle point at the origin. I guess properly speaking, I should say f of 0, 0 is a saddle, and f of 1, 3 is a local min. Okay, so now we'll take this and apply it to some more complicated examples.